The Charles Hatchett Award 2016 lecture is about development of niobium boron grain refiner for refining the grain structure of aluminum silicon cast alloys. This was initially a PhD program of Dr. Magdalena Novak. Later on, Dr. Leandro Bolgioni progressed this work further, where the master alloy is developed and applied to these cast alloys. This is one of the major research programs within the liquid metal engineering over the last 4 years or 5 years at the Brunel University. The outline of my presentation is that I will introduce basically the grain refinement, the current practice of the grain refinement in aluminum alloys using titanium boron grain refiner, and discuss how the concept is developed, and some results on how the aluminum silicon cast alloys, its application, and early stage work on the aluminum niobium boron master alloy development. Finally, we compare the results between the niobium boron and titanium boron master alloys. Aluminum alloys are the light in their density. They are about 2.5 grams per cc. They have good mechanical properties, high corrosion resistance and thermal conductivity properties, low electrical resistivity. Because of these specific properties, and also the material is highly recyclable and it's being used more and more annually. These aluminum alloys are categorized into two groups. One is the wrought product, another one is the cast alloys. Wrought alloys are basically the low concentrated alloying elements, and initially they are produced using the direct chill casting large billets, and these billets are rolled into sheets or extruded into extrusion profiles. For this, during the downstream processing, the billet needs to have a specific properties, then it can produce the better results. So that's where the grain refinement is playing a very important role. Aluminum titanium boron grain refiner is effectively used, and it's a very well established industrial practice. The benefits for the grain refinements are that it improves the castability, machinability, and provides the better chemical homogeneity across the billet. Also could improve the mechanical properties, improves the surface quality, and obviously reduces the shrinkage porosity. For cast alloys, majority of the cast alloys are based on the silicon as an alloying element. For this cast alloys, titanium boron grain refiner is still being used to a certain extent, but it is known to be not effective, and this lecture is about developing the material right suitable grain refiner for that particular one. So there are two factors which governs the grain size of a cast material. These are the nucleation and the growth. Nucleation is the one which at the early stage, that's the one which dictates the overall microstructure. Growth is associated with the processing. So the temperature can influence the growth rate. Cooling rate can ignite the more nucleation density within the liquid metal. You could also adopt the changing the pressure or atmosphere in the material to change the growth velocities. By introducing the alloying element in a material, you could either restrict the growth or enhance the growth rate. So there are many ways you could change the microstructure. And also, while solidifying this liquid metal, if you apply external fields such as electromagnetic fields or ultrasound or shearing, you could actually fragment these dendrites and get the finer grain structure. But for a given process and for a given alloy, the only thing that what you have to look at is the introducing the heterogeneous nucleation sites into the liquid metal, so that it helps the reducing the undercooling. That means these crystals are grown at the lower growth rate, so overall it can end up in having a very good refined microstructure in the material. So to have a best efficient heterogeneous nucleation site, it should have three characteristics. Obviously, it should have a high melting temperature, and it should be very chemically stable with the liquid metal. And most important parameter other than these two are the lattice mismatch. The lower the lattice mismatch it is, the lower the undercooling, so that you could get a finer grain structure in the materials. Aluminum titanium boron grain refiner is most commonly used for wrought alloys, and the right side what you see there is the transmission electron microscopy showing aluminum nucleation on TiB2 particles. If you look at closely between the aluminum layer and the titanium boron layer, you have the aluminum 3 titanium layer. So what it means is that the aluminum 3 titanium is more potent substrate for the aluminum in comparison with the titanium boride. So presence of the both TiB2 and Al3Ti particles in the master alloy is the key to produce the better grain refinement. So this is what the traditional TiB grain refiner has. To modify the silicon morphology, strontium is used, very well used. And to reduce the silicon particle size for hyper-eutectic alloys, phosphor is used as a nucleation site. If you use the titanium boride grain refiner for aluminum silicon cast alloys, the x-axis is the weight % of silicon and the grain size, and 3 curves represent 3 different levels. As you increase the titanium concentration, it refines the grain structure very well at a low silicon containing alloys, which are the wrought alloys. But for the cast alloys, this particular one is shown to not to be very effective. The main reason why it is that the titanium reacts with the silicon, and whatever the titanium is acting in refining that one, that characteristics we are losing. This is usually referred as a poisoning in our literature. So here is the ternary phase diagram between aluminum, titanium and the silicon, where you can see the more the titanium we put, the more the silicon it has, the titanium silicide phase formations occur at the lower temperature. So our research program there is that can we develop an alternative, initial plan was only to develop an alternative grain refiner to see what's happening to these aluminum materials. So when we looked at the phase diagrams, we found that the niobium has got an analogy to the aluminum titanium. So the phase relations between AlNB and AlTi are very similar. So both are the peritectic systems. Both have got the aluminides, Al3NB in the niobium case, Al3Ti in the titanium case. So this one is, there is a lot of information, but please only focus on the red one, which is Al3Ti, and the blue one is Al3NB. Their lattice parameters are very close. Both are the tetragonal phase, and if you look at the basal plane of Al3NB and the basal plane of the FCC structure, both have a very good close lattice parameters. As a result, you can see that the lattice mismatch between Al3Ti and aluminum is 4%, between Al3NB and the aluminum is 4%. Here, between niobium boride and the aluminum, or titanium boride and aluminum, there is a large mismatch. So what it means is that here the titanium boride nucleates the Al3Ti, Al3Ti nucleates the aluminum. Similarly, niobium boride nucleates the Al3NB, and then that's the analogy. So here is the transmission electron microscopy of aluminum niobium master alloy. This one is a Al3NB precipitate, and the Fourier transformation shows that there is a nice lattice mismatch, less than 1% in this particular orientation. So that suggests that Al3NB can act as a very good nucleation site for aluminum alloys. In addition to this lattice parameters, we have to look at the chemical stability with silicon. So niobium also reacts with silicon, but the reaction temperatures are much higher than the aluminum titanium based one. This ternary phase diagram on the right side, if you see niobium and silicon and titanium and silicon, you can see very clearly that titanium silicides forms at much lower temperature, the temperature close to the casting practices, whereas the niobium at the casting practices are usually at 750 degrees. So the niobium silicides are not expected to form. So this is our motivation, 2 motivations. One is that Al3NB has a lattice mismatch, and also niobium has a more phase stability with the silicon. So based on this, we applied this work to the aluminum alloys. So initial results are that when you introduce the niobium metal powder into liquid aluminum, because of the higher density of the material, so niobium just remained at the bottom. So we did have some grain refinement. If you look at closely the particle, undissolved particle, there is a layer Al3NB, NB2Al, Nb3Al, which it means is that under that certain processing conditions, this is not completely dissolved. So in order to dissolve this particle, you have to stir the liquid metal as much as possible so that it can be dissolved quickly. So there is a grain refinement effect which we could observe more effectively. So what we have adopted is that instead of going for the coarser particles, we introduce the finer niobium particles less than 45 micrometers, and also we introduce the boron as a flux, so basically to form the niobium boride. So what we have here, the y-axis is the magnetic moment measured using the squid magnetometer, and the x-axis is the temperature. Because the niobium is a superconducting material, which with the 9 Kelvin transition temperature, if you have the niobium, unreacted niobium, it should give us the superconductivity signal. That's what it is shown here. If niobium dissolves completely and forms the Al3Nb, we don't expect to have a superconductivity. That's what that is confirmed. So in the combination of niobium and boron, we have some inclusions that are formed in the material of NbB2 and Al3Nb material. So initial results are that the commercial pure aluminum, Cp stands for commercial pure. This means that this particular mold is called test procedure 1. This is widely used across every industry. Use the same mold as a reference or a standard test. This one is the niobium boron grain refiner and the commercial aluminum. You can see the refinement is taking place. Here is a comparison between the titanium boride and niobium boride. The black one is without any addition, and this is the pouring temperature. The higher the pouring temperature, the more large temperature gradient within the solidification place, whatever is happening. So it's a coarser grain structure occurs. Whereas when there are nucleation sites within the liquid metal, these high temperature or superheat doesn't play much role. You get the finer grain structure. If you see here, the blue one is the titanium based grain refiner, and the red one is the niobium based grain refiner. For wrought alloys, titanium is very effective, much more effective than the niobium, and there is not much exciting feature in that particular one for us. Then what we applied this material to the various aluminum silicon binary alloys, 1 silicon, 2, 4, 6, 8, 10. For the titanium boride is shown here, for the niobium boride shown here. If you look at these areas at high silicon containing alloys, the niobium is shown to be performing better than the titanium. Here is the summary of that result, where the silicon content versus the aluminum grain size. The black one is without any addition, the curve. The red color symbols are for the titanium based one. For wrought alloys or the low silicon containing alloys, titanium is very effective than niobium, but at high silicon containing alloys, where most of the practical alloys, you have a very big difference in this one. This is where the key interest for us to explore further. So the high silicon alloys are typically used to produce this type of automotive applications, engine transmission components, chassis components, structural components, wheels, and this type of one. If the niobium boride or Al3Ti is acting as a heterogeneous nucleation site, it should reflect in the reduced undercooling. For that, we designed an experiment to measure the undercooling for aluminum 10 silicon alloy. So this one is the temperature as a function of time. The undercooling is here the liquid metal starts solidifying, so that the heat is released. So this undercooling is about 2 Kelvin. Under these conditions, where 0.3 Kelvin per second is the cooling rate, you get around 1 centimeter size crystals within the melt, and this is the thermocouple that we placed in this one. And by introducing the niobium boron inclusions into that one, the undercooling is reduced to 1.3 from 2.1. That suggests that these particulates are acting as a heterogeneous nucleation sites and giving us the addition rate is the 0.018% of niobium. They are very low addition rates. And then the similar one is for aluminum 11 silicon alloys, where the thermocouple there, and then the niobium boride undercooling is about 0.7 Kelvin. Then we continued this work for hyper-eutectic alloys. So for the eutectic composition is about 12.6%. Primary silicon particles form, and we also have some, because it's a non-equilibrium solidification, we still have the primary aluminum dendrites. So those primary aluminum dendrites we can still see the finer, and we further expanded this work to see what is the eutectic silicon, how it gets refined. So what it means is that when we introduce the niobium boride, eutectic silicon particles size reduced significantly. 16, 18 and 27% silicon, and primary silicon particles are also, their size is also decreasing. This is more effectively seen at lower silicon additions. At high silicon additions, the grain size of the silicon particles are quite similar, whereas at the lower silicon levels, where we have a much finer primary silicon particles. And now I would like to discuss about the application of niobium boron grain refiner for commercial alloys. So far what we have done is for the binary alloys. The commercial alloys that what we have studied so far is the 6% silicon to 13% silicon. Various alloys are tested, and these ones are the commercially known products, whereas this one is done with the industrial collaboration with various industries, this particular one. So niobium boron grain refiner for aluminum silicon cast alloys, we think they are highly effective for these alloys and also for magnesium alloys. We are not focusing here on magnesium alloys, it's mainly for aluminum silicon cast alloys. Here is the industrially known, very well established commercial alloys, LM25 typically used for wheels, LM24, LM6. This one is for the reference, aluminum titanium boride and the niobium boride in this case. Here in all these three cases, what you see is that in all conditions, in all alloys that we have studied, is the niobium boride is always shown to refine the grain structure, unlike the titanium boride materials. So as a result of the grain refinement, we have in addition to the fine grain structure, we also have uniform grain structure in the material. So this one is the wedge-shaped mold, where the cooling rate of the wedge mold at around this 1 centimeter from the tip here is about 100 Kelvin per second, and here about 50 Kelvin per second, and here about 10 Kelvin per second. The lower the cooling rate it is, the coarser the grain structure. The grain structure increases from 200 micrometer to 1.2 millimeters. And also you have the porosity in the material. And then by introducing the niobium boride, whether it is a thin section or thicker sections, you have the very fine grain structure in the materials. And the grain size is less sensitive to cooling rate. That's what I will describe here. This low cooling rate about 0.3 Kelvin, 1 Kelvin per second, and 3.5 Kelvin per second. And two alloys we compared, one is LM6 and another one is LM25 alloys. So at lower cooling rates, there is a huge difference in terms of the grain refinement. At the higher cooling rates, the difference is relatively marginal. And the same thing here, we actually measure the grain structure more closely, up from 0.3 Kelvin to 100 Kelvin per second. With the grain refinement, it's very similar whether you cool very high cooling rates or lower cooling rates, whereas for the reference materials at the lower cooling rates, very huge grain structures form. What it means is that if you produce a casting which has got a thicker sections and thinner sections, with the addition of niobium boride, you can have a similar properties in everywhere. That is the very useful when they design the new component for the automotive or any other applications. So this is the data extracted from the previous curve. What it shows here is the number of grains as a function of the cooling rates. Higher the cooling rates, the more number of grains per unit volume. In the case of addition of the inoculants, it's still even higher. The the x-axis, y-axis here, the first one what we have here is basically the efficiency of the material. It's very effective at low cooling rates. As you go into the higher cooling rates, it's relatively marginal in grain structures of the material. Because, as I said, it's a low cooling rate, it's very effective. We try to do the sand casting cooling conditions, and in that particular case, produces very better grain structure. This is the riser area for no grain refinement, and this is with grain refinement, where you can see the large structures. And at the tensile bars, by adding the niobium boride, about 3 or 4 millimeter size crystals reduced to their size to about 250 micrometer size one. In that area, here is the microstructure. This is a large aluminum silicon primary aluminum dendrite, and the refining the grain structure. This is about 9% silicon containing alloy. As a result of the grain refinement, what happens is that if you have a large dendrites, when the solid is solidifying, the eutectic liquid is ejected. This needs to be adjusted within the melt. So if you have a larger dendrites, they lock the liquid doesn't feed into the system. You end up in having the porosity in the materials. So that's what we see here. The aluminum 11 silicon alloy without adding the grain definer, the titanium boride grain definer, and the niobium boride grain definer. The major thing that what we see, in addition to the grain refinement, we have a very negligible shrinkage porosity in the materials. This will give us better ductility in the material. This is the LM25 alloy. Here also you can see the lower porosity. This is the porosity area of the porosity in a given surface area. The titanium boride grain definer also helps reducing it, and this is even better kind of one. This is an alloy which is used for a wheel applications, and you can see the porosity can be reduced significantly by introducing the grain definer. Then once the primary alpha aluminum solidifies, the remaining liquid is mainly eutectic composition. So because these primary dendrites are scattered everywhere in more homogeneous way, you expect to have a relatively very small eutectic pools. As a result, eutectic structure also should modify. So what we have here is the eutectic silicon for aluminum 11 silicon alloy, and the eutectic silicon in the case of niobium boron addition. Very clearly that the refinement of the eutectic silicon is also happening. And this is happening at wide range of cooling rates. When we say wide range of cooling rates, what it really means is that the aluminum alloys are cast using high pressure die casting, very high cooling rates, low pressure die casting, relatively lower cooling rates, sand casting where it's even lower cooling rates. It is shown to refine the eutectic silicon at wider processing techniques that are adopted in industry. This is the aluminum 10 silicon alloy. It's just the binary silicon alloy, where you can see the eutectic needles and you can have a very fine refinement. And this is the piston alloy, where this is the hyper-eutectic alloy. You have the primary silicon particles. Because it forms the large dendrites, the primary silicon particles gets formed, trapped in between these primary dendrites. And in the case of niobium boride, they are more uniformly dispersed. As a result, the wear resistance of this one is expected to be performed better than the traditional material. In addition to the refinement, in addition to the grain size, we also have the refinement in the eutectic silicon as mentioned in the previous slide. So because we have the primary aluminum grain refinement and also the improvised eutectic structure, these should result in somewhat the improved ductility and the strength for the material. We measured on LM6 alloy, where aluminum 11 silicon containing alloy. This one is the ultimate tensile strength as a function of elongation. It scatters around this one, and in the case of niobium boron grain refiner, both the strength and elongation is improved. The yield strength, this is what generally is used to design the component, is also improved by about 15% for this alloy. And then we repeated the similar work for aluminum 13 silicon alloy, piston alloy. Here also you could see the improvement in the tensile strength and the elongation. These are the earliest work that what we have done in the laboratory scale. The aluminum industry always, all the aluminum parts are usually combined with the steel based one. So when the material goes into the scrap, the iron enters into the aluminum scrap. So this iron forms a very long needle structure as an intermetallic with aluminum, Fe, silicon. These needles or intermetallics are very brittle. They are so brittle that once you have these beta phase particles formation, they just become highly brittle, and also reduces the tensile strength of the material. So what we have done here is that, as we know that it can help refining the eutectic structure, we wanted to see how iron is getting modified using this niobium boron refiner. So this is the base alloy. When you introduce 1% iron, you have this needle structure one. These are the needles which are highly brittle, and by introducing the niobium, about 0.1% niobium and 0.05% of boron, you could see these about 500 micrometer sized long needles can be refined significantly in this case. As a result, the mechanical properties of a virgin alloy are this one. By introducing iron, the ductility and also the tensile strength goes down. This is known fact. Because they are refined beta particles, the properties that are lost due to the iron contamination, we can recover those properties. What it means is that the materials treated with the niobium are more tolerant to iron contamination. So this is one of the major future application which is expected to recycle the aluminum scrap for high value applications rather than the downgrading the material. In industry, once you have the grain refinement, they would like to know, for example, how long this performs, whether does it fade over the time, or when you remelt the ingot, does it actually produce the similar microstructures or not. For that, we performed the fading study in the powder edition case, not the master alloy. We did see some fading structure, but it is well below the base alloy that microstructure it provides. The later work which we did with the master alloy shown to not to fade up to 7 to 10 hours. So what it means is that the fading does occur depending on the particle size that it forms. So here I give you an example of the time required to sediment this one. So the sedimentation height, if you take a 20 centimeter crucible and if you inoculate that one, if the particle size is about 20 micrometer, they only take about 6 hours to sediment. If it is a particle size about 15 micrometer, you can extend the time that required. And aluminum 3 niobium takes much longer to sediment. So overall, what this slide tells us that this refiner does fade, but you need to wait for at least 6 to 10 hours to see the fading result. So it is easily adoptable in industry. That is the main key point here that I was to mention. So the remelting, what I mean is that once this is the base alloy, apply the grain refiner, cast it, and then remelt that one and cast again, remelt this and cast, remelt that. And so over the time, how the grain refinement, the performance is. As you could see, the grain refinement continued until 4 remelts that what we have done. That means if the ingot is produced with the niobium containing material, when it goes to the industry, when they recycle, the melt and cast it, and then again melt and cast it, it still retains their grain refining performance. That is an important aspect for the industrial one. Then the master alloy development. Most of the work what I showed you is the niobium and boron addition in the form of powder, majority of those results. Here I show you the lab-based master alloy development. We follow 2 different methods. The first method is simply introducing niobium metallic powder and the boron-based salt to liquid aluminum and then leaving there for 2 hours, stir it and cast it. The recovery of niobium boron in this case is very low, but you can still see the fine niobium based particles. And we try to look at what they are. They do contain the niobium boride and also aluminium 3 Nb, what I initially expected to. The second method is where if we take the boron, aluminium boron master alloy, dilute it and introduce the niobium into it. In this case, we could have a better recovery of niobium and boride based inclusions. As you could see, the hexagonal niobium boride inclusions in the material and also the Al3Nb materials. So from now on, I show you a series of micrographs, the influence of the master alloy addition on the aluminum silicon alloys. LM25 has got 7% silicon. This is the reference alloy, and niobium boron master alloy. This is the powder addition. Powder addition is shown to have a better refinement compared to this. That is at the early stage of the work what we have done. And by here, as a function of niobium boride 8% and the aluminum grain size, you can see that the grain structure is keep decreasing as you increase the boride structure, as is expected in the materials. Then we produce the 2 niobium 1 boron based master alloy, different types of concentrations. So all of them are shown to refine the microstructures of the aluminum silicon cast materials significantly. So if the master alloy has because the recovery in the second method is better, so we try to see its influence on undercooling in various aluminum silicon alloys. Here 7 silicon alloy, 9 silicon alloy, 10 silicon alloy. In all cases, what we see is the undercooling in the case of reference material is 1.7, and when you introduce the niobium boride based inclusions, it's decreased. What it means is it is shown reproducibly that all sorts of cast alloys where the silicon content is above 7% or 6% are significantly getting refined. Here is the wedge casting. It's the same story as the powder addition, that it is it's not very much sensitive the grain structure when you add the refiner, and in the cylindrical case you can see the very large dendrites, and by producing the master alloy very smaller dendrites in hyper-eutectic alloy. And this is the previous one is the hypo-eutectic alloy, and this is the hyper-eutectic alloy. The hyper-eutectic alloy typically used for piston applications or wear resistant applications, engine cylinder heads and things like that. So here you could see that the coarser grain structure and the finer grain structure. And this is a summary slide to show different silicon containing alloys. When you add the grain refiner, they are insensitive to the silicon content, unlike in the base, the reference. As you increase the more silicon, the larger the grain structure. This is the cooling rate as a function of the grain size for wide range of silicon cast alloys. In all cases, what we have seen is that it is very less sensitive to the cooling rates. That means if you produce a material produced in low pressure die casting can give you the microstructure very similar to that of the high pressure die casting. So what it means is that the material properties are expected to be more better for the low cooling conditions based one. Even in high pressure die casting, we still have the refinement, and it is expected to produce the improved ductility and some strength in the material. High pressure die casting is one of the largest or very commonly used manufacturing process in the aluminum industry. Here we apply the grain refiner for DC casting facility, DC casting billets. The direct chill cast billets are the ones which is commonly used. The process is commonly used for wrought alloys. So aluminum 10 silicon alloy, although it is not classified as a wrought alloy, but it is typically produced using the direct chill casting, because if you want to use it for brazing application or the soldering rods, it is produced into a billet and then rolled or extruded. So you have if you don't have the refiner at the chill zone, you have the very fine crystals. Because the heat extraction is in this direction, you get the columnar grain structure. When we introduce the niobium boride about 0.1%, extremely fine uniform grain structure across the billet, and even at the lower content you have the equiax. This is the microstructure that is the desirable for producing the better the wrought product for this one. And we depicted the same thing here in schematically, that the chill zone and the columnar crystals, and in the case of niobium, very equiaxial crystals. The benefit of this one is the chemistry is more uniform across the billet, unlike in this case. So here is the microstructure taken at a different levels, chill zone, very fine crystals in both cases. But as you grow further deep inside, you have a continuous columnar structure, and again the columnar to equiax transition zone, coarse columnar to equiax, coarse equiax crystals and fine equiax crystals across the whole billet. So this is the one application where the niobium boride could give the better opportunity to produce the aluminum tin silicon billets for brazing applications and things like that. So finally, we have two more slides here, describing the comparative study between the master alloy, aluminum niobium master alloy and titanium boron master alloys. Here is the aluminum tin silicon alloy. If you cast under certain conditions, exactly the same cooling rates, introducing the 2 niobium and 1 boron, you can see the very fine grain structures. We introduce the similar level of titanium, we have the very coarse grain structure. We also increase the titanium concentration even higher, it's even coarser than this material. So what this slide tells us that for aluminum silicon cast alloys, niobium boron is highly effective one. And this is another case where the alloys that are typically used for wheels is aluminum 7% silicon and 0.3 magnesium based alloy. The reference has about this one, and this is a typical industrial practice addition rate. Is still the similar grain structure. By introducing the niobium and boron, you could see the very fine grain structure. By introducing large concentration of titanium, is still the coarser grain structure. So in summary, what we think is that over the last 4 or 5 years, we found that the niobium boron addition to aluminum silicon melt refines the grain structure of casting, and we expect that there are several end user benefits, which one is the improved strength and ductility. That means lightweight components, thinner sections can be produced. The homogeneous properties, which means thin and thick sections, so that you can produce the complex structures, and tolerant to iron contamination. So the niobium boride is enhancing the tolerance levels of the iron. What it means is that closed loop recycling of scrap containing higher iron is possible. Because the reduced shrinkage porosity is consistently observed in many cases, it is shown to improve the soundness of the bulk casting. So which means that the component rejection ratio can be minimized in industry. So this is the overall work that what we have developed over the last few years.